Hello everyone, welcome back to Deviations. In this video of single variable calculus, we will be covering the mean value theorem. This is one of my favorites to talk about in Unit 3, and it's really the capstone of our build-up in the past two videos with maxima, minima, and Rolle's theorem. So this is really an extension of Rolle's theorem that's going to give us some extremely powerful tools when we start working on some word problems later on in this unit. As always, I recommend if you're rusty on differentiation, you check out my Unit 2 videos on just the methods of differentiation, and you should be good to go with Unit 3 after that. Otherwise, let's get started with talking about the mean value theorem. So, I'm just going to start by putting the theorem in its purest form, and then we will cover a geometric approach to it. So, given f is continuous on AB and differentiable on AB, then there is a number c in AB such that, firstly, f prime of c will equal f of b minus f of a over b minus a. Secondly, it will be f of b minus f of a equals f prime of c times b minus a. Now, of course, the second is just a rearrangement of the first, but that will be very helpful for us in some examples that we are going to do later on. Okay, so a couple of things we can talk about here. First of all, this looks a lot like a secant line approximation that we've been dealing with when we've been defining the derivative and trying to average slope back in high school. So that should be familiar. And that's going to lead us really nicely into our geometric approach. So let's say I have a coordinate system here, normal xy coordinate system, and I have a function here, and I'm going to define it on an interval from a to b. So there's a and there's b. What the mean value theorem says is that if I draw a secant line from a to b, if I draw my slope approximation, let's call that m average from a to b, there is going to be a point, there will exist a point C, there will exist a point C, probably in this case about here, where I'm going to have a tangent line. I'm going to have a tangent line. And that line at f of c, the slope of the line at f of c is going to be the same as the slope of my secant line. So that should really bring some more light to the actual naming of this theorem, the mean value theorem, because it is comparing a derivative to a mean value approximation that we take from our secant lines. All right, so now that we are armed with this new theorem, why don't we do an example? We are going to go back to James Stewart's Calculus Early Transcendentals book, and we're going to take an example from there. We're going to do example 4.2. From section 4.2, we're going to do example 3. So this example, they're telling us to consider a function f of x equals x cubed minus x on an interval 0, 2, where the mean value theorem will apply. So we are going to apply the mean value theorem. So what should we do first? So first, we should set up our theorem. So we saw the equations in the previous slide. So let's write this out, but let's specify it for this example. So we're going to take f of 2 minus f of 0 equals f prime of c times 2 minus 0. Now, of course, we are going to want to know our endpoint values, as we need to take f of 2 and f of 0. So f of 2 is 6, and f of 0 is 0. And we also should know our derivative, and our derivative is going to be f prime of x equals 3x squared minus 1. And of course, that is just some simple polynomial differentiation that we covered a while ago. Okay, so now we are going to simplify the equation that we see here on the left-hand side. And we are going to get 6 equals 3x squared minus 1 times 2 equals 6c squared minus 2. Okay, so now we can solve for c here, and we will get that c squared equals 4/3. And of course, that will mean that c equals plus or minus 2 over root 3. However, because our interval is from 0 to 2, we are going to have an extraneous solution, meaning that we can take the positive c equals 2 over root 3. And that is our example. That is our final result. Okay, so now let's talk about some extensions of the mean value theorem that can really help us understand the deep intuition behind some of the derivatives we've been doing back in Unit 2. So, first of all, given f prime of x equals 0 for all x in AB, then f is a constant on AB. Okay, so what is this saying? So this is basically that constant rule that we talked about a while ago, and it says that if I have a constant function like that, and it doesn't matter how high it is off the x-axis or how low it is behind, it's always going to have a slope of 0. F is a constant on AB if the derivative is 0. Excuse me. So that is what one of the deductions is from the mean value theorem. Now we have some other ones. So this one says if f prime of x equals g prime of x for x in AB, then f minus g is a constant where f of x equals g of x plus c. Okay, so that's saying that if my derivatives are the same, then that means that if I have a function x, if I have a function g, they're going to be the same function, just they're going to be at different levels. Okay, so let's try to prove this. So we're going to prove this through making function capital F of x equals f of x minus g of x. Okay, now if I differentiate this, I'm going to get f prime of x equals little f prime of x minus g of x equals 0 for all x in AB. Now, of course, this proves that our derivative is 0, and it proves the theorem that we talked about earlier, meaning that f is a constant, implying that f minus g is a constant if it is equal to f. Okay, so that was another theorem that we can deduce. Let's do one last example before we finish off. So we are going to do from section 4.2, example number 6, we are going to prove that the arctangent of x plus the cotangent plus the arccotangent of x is equal to pi over 2. All right, so first what we can do is we can have our given. So if I'm given f of x equals the arctangent of x plus the arccotangent of x, then f prime of x will be 1 over 1 plus x squared minus 1 over 1 plus x squared. Of course, we need to remember some of our older inverse trig function differentiation formulas, and that equals 0. Okay, therefore, f of x equals c if our derivative is equal to 0. So c will be f of 1, and that will be the arctangent of 1 plus the arccotangent of 1. Meaning pi over 4 plus pi over 4 equals pi over 2. Now that is our last example for the mean value theorem. Thank you for watching. Please like and subscribe, and we will see you in the next video where we will start to discuss concavity and how we are going to be able to use the derivative to graph functions. See you then. Bye-bye.